Yeah, here we are. Everything is organized. So if you have any questions, just don't be shy. You have a perfect opportunity to ask your questions. Just don't be shy, because good online is when you ask questions.
Sorry, I
If
have a
something
question.
was not clear, or you have any questions maybe outside the scope of the course, that's okay.
Stepan, go on.
Mhm.
I think we have the same question.
Thank you, Kirill.
You're welcome.
You told us
So
yesterday.
let's continue with cookbook procedure for
Stepan has a question.
solving inequality optimization problems. So today
Sorry.
we will present.
Sorry,
Sorry,
Stepan
Stefan.
has a question.
You cannot hear me.
Давай уже.
Yeah.
Yeah, Борис, you told us yesterday that you were going to upload the last lecture.
Yeah. I have uploaded everything. So now I need to, because I have a lot of classes, lectures. So I have uploaded. Yeah, this night I have uploaded all the past materials, and I have started to do. I have created playlists, and I have started to classify. After this lecture, I will finish classification into playlists, and so everything is okay. That's already downloaded from YouTube, or downloaded from Zoom, already uploaded to YouTube. And so I have created playlists, and I just need to publish and click, choose a good name, but it takes time, because sometimes it cannot be done automatically. Just I need
Okay, great. Okay,
yeah.
thank you.
So yeah. I remember I have already downloaded and uploaded. Okay, cookbook procedure for cookbook procedure. So last week we have covered intuition behind first order um, first order necessary conditions for optimization. And now let's discuss like algorithm, what we do. We have a so first step is just it's real advice. It's real advice. Avoid optimization with inequality constraints if possible. So that's a real step. Avoid optimization with inequality constraints if possible. Never, if it's possible. Sometimes it's necessary to use them. So, and this advice is not only for exam, but for real life. I don't know, some, if you will estimate some complex econometric models, or I don't know, machine learning models, that's a good advice. Avoid optimization with inequality constraints. So on the exam, so this advice is both for exam and for numeric optimization with computer. So for example, if once again, that's a real advice, do not forget it. I'd like to stress it. That's a very good, important advice. If you have something like maximize x squared plus y squared, given that x is greater than 0, y is greater than 0, x squared or 2x plus 3y is less than 15. So if I have such a problem, and I have no, because sometimes on the exam they may be required that just use Lagrangian procedure with inequality constraints. So if I'm not required specially by the text of the problem to do optimization with inequality constraints, then I clearly see that in that case, I see that I would like to have x as big as possible. Y, I would like to have as big as possible. I would like to increase x. I would like to increase y. My function depends on x and y positively. And so in this case, I see that a point with 2x plus 3y less than 15 is certainly not an extremum point. Why so? Because if I have 2x plus 3y less than 15, then I can increase x, and I will have bigger x squared plus y squared. So in this case, I just replace my function with maximum s squared plus y squared subject to x bigger than 1, y bigger than bigger than 0, y bigger than 0, and 2x plus 3y equals to 15. So I have replaced inequality constraint by equality constraint, and that will simplify greatly first order conditions. So first advice, avoid these problems as much as possible. Sometimes it's not possible. Sometimes it's not obvious whether the condition will be satisfied or not satisfied as equality. In numeric optimization, often you have, I don't know, you optimize some complex model and some probabilities inside when you are doing some forecasts in time series Markov chain switching models, and you have that probability is between 0 and 1. It's one of millions of parameters, and you have inequality constraints. But in that case, you may say that just, yeah, I will replace p by exponent of t divided by 1 plus exponent of t. And I have created such a function, such a transformation to make it between 0 and 1. And t now is any real number. So I have replaced bounded parameter by unbounded parameter. And I will do optimization with respect to t, not with respect to p. So that's a really important idea, that optimization problems with inequality constraints are tough on paper and numerically. And it's better to avoid them on paper and numerically. So that's the first step in Cookbook procedure. Avoid these problems if it's possible. Sometimes it's not possible.
Can I ask you a question?
Yes.
What do you mean by avoid? Like,
I have explained.
Yeah, what do you mean by...
I'm required in the exam to solve that problem. I say my argument, and I solve this one. I have a problem with equality constraint and not with inequality constraint.
Okay, I see now. Okay.
So avoid, do not solve them if it's possible. Avoid.
Well, you mean do not solve them, but basically change them? Yes.
So yes.
Okay.
So, or if you have, so my basic idea that problems with inequality constraints are tough if you solve them on paper, or even if you solve them numerically on computer, they are tough. They're hard to solve. And there are tricks to transform them into problems with equality constraints. So in this case, I see that my goal function, x squared plus y squared, depends positively on x and y. So I would like to have x as bigger as possible, y as big as possible. And it cannot be that 2x plus 3y is strictly less than 15 in this setup, because if it is like that, then I will just increase x, and I will not violate my constraint, and I will increase the value of my function. Okay. Yeah.
Yeah, thank you.
Okay, and this advice applies also to real life problems with computer. If, for example, I have that often happens in machine learning models when you have a Bayesian approach or some maximum likelihood algorithms, when you have probability, and probability normally it should be between 0 and 1. And to avoid using these bounds, I will just replace p by a function of t, and for any t, the resultant p, my choice of transformation is such that automatically these two bounds, 0 and 1, will be satisfied. So that's a standard way to solve some probability problems optimization on computer. Okay, that's the first step. Okay, now second step, standardize the problem. What do I mean by second step, standardize the problem? So if you cannot avoid, then okay, let's go. What do I mean standardize the problem? I will always solve maximization problem when you have some constraints. My constraints will be, what do I have here? Some strict inequalities. I don't care about their form because they will not enter, they will just be copied in first order conditions. So strict inequalities, any form is okay. Now I will have some equality constraints like h. So I will have f of x, x2, xn. So I have h1 of x. X is a vector, yeah, because I have a multivariate problem. X is a vector. h1 is 0. h2 of x is 0. Some of them. So I have equality constraints. And now I have some inequality constraints. G1 of x is greater than 0. G2 of x is greater than 0. So what do I mean by standardization? I will always write maximum. I will always write greater or equal than 0. I will always write greater or equal than 0. So if you have some, I don't know, other problem, so imagine that I have something like I need to maximize x squared plus y squared subject to x squared plus y plus 2x is less than 5. I will transform it into maximize x squared plus y squared subject to. I can always write this inequality like something in the left hand side greater or equal than 0. So I will standardize all the inequalities. So imagine that I have two inequalities, x plus y greater than 1. So I will standardize all the inequalities. The first will be 5 minus 2x minus y minus x squared greater or equal than 0, and x plus y minus 1 greater or equal than 0. So what do I mean by standardization? I will always have maximization problem. I will always have inequalities of type something is greater or equal than 0. So I standardize the problem. Okay, any question? Yeah.
Yeah, if we standardize always with max, what do we do with min?
imagine that you would like to have minimization of minus x squared plus 6x plus y squared minus z, subject to x plus y plus z is greater than 5. Oh, sorry, 5. I can always I will say maximize x squared minus 6x minus y squared plus z, subject to x plus y plus z minus 5 greater or equal than 0. So when you are searching, so if you just reflect the function, the bigger how to go from I'd like to have the smallest possible value of function, but my function is negative of yours, and I would like to have the biggest possible value of the negative function, but my function is negative function compared to yours function. And so we are searching the same thing.
Okay, thank you.
Okay, so basically every problem, do not memorize many conditions, because otherwise you will need to memorize a lot of conditions. You will need to memorize condition for maximum, condition for minimum, and so on. We have discussed last week that first order conditions are different. And if I use standardization, then I remember only one condition for maximum, for inequalities like that. I don't care. So, because if you do not standardize, then okay, you may not standardize. It's my, basically this cookbook procedure is my recommendation. It's not a must. So, if you'd like, you can memorize conditions for minimum, for maximum, for minimum with inequalities greater than 0, for minimum with inequalities less than 0, for maximum with inequalities greater than 0, for maximum with inequalities less than 0, but to not memorize 4 different types of conditions, because you may have inequalities greater than 0, less than 0, maximization, minimization. I will always transform to maximization greater than 0. Every problem I have, maximization greater than 0. And that's why. Honestly speaking, you may even you may skip this step, but the first order conditions will change if you skip this step. Okay. Okay, I pretend that was okay. Now, let me discuss in brief third step, fourth step, and the step number 5, and then we will go on the example. So check in DCQ. So write Lagrangian function, but I don't care. I don't know whether should I separate these 2 steps. Okay, let's say solve first order conditions, and after solving the first order condition, you may check that the point is minimum, maximum. So classify, let's say classify suspicious points. Okay, so basically we need these 3 steps to complete. Check non-degenerate constraint qualification conditions, solve first order conditions, and after we have obtained suspicious points, we need to say whether they are maximum points or minimum points. Okay, let's I will start from a blank page. Okay, let's consider example. I will create a more or less complex example with 3 variables. So I would like to maximize x plus y plus 2z subject to, or maybe minimize. Yeah, let's start with maximize. Subject to x squared plus y squared plus z squared is less than 10, and x plus y plus let's have plus 2y plus z is equal to 0. Yeah, let's do like this. Everything is fine for the moment.
It's okay. Thank you. Let's carry on.
Okay, so I will. So I have 2 goals. Basically, the first goal is to show what to do when no simplifications are possible. And the second goal is to show you that if possible, then simplify. So on real exam, what I will do on real exam, when I have this problem, certainly I will decrease the number of variables. So on real exam, I will say, oh, that is equal to minus x minus 2y, and I will plug in equations and constraints, and I will have maximize x plus y plus 2 minus x minus 2y subject to x squared plus y squared plus minus x minus 2y squared less or equals than 10. Okay, for sure, I'm sure that this is much simpler. I have 2 variables instead of 1. I can, when I have 2 variables, I can solve second order conditions. I can check whether the point is indeed maximum or minimum point using graphs. And in 3 dimensions, it's less. I can draw some projections. You have done even a home assignment with 3D plots, but it's better to do 2-dimensional plot than 3-dimensional. So on real exam, I will obviously decrease the number of variables. So decrease the number of variables. But for the moment, I will say that imagine that I cannot decrease the number of variables. Maybe the equation is too complex, is very tough equation, or maybe it's required in the text by the author of exam. Use Lagrange multiplier methods with 2 multipliers. And so sometimes I have no possibility to decrease the number of variables. But first idea, simplify if possible. Simplify if possible. That's a good advice. But imagine that I have skipped the opportunity to simplify. Maybe I just missed it. I forgot that I can simplify, or it was written in the exam text. Just use Lagrange multipliers with 3 original variables. And so I can simplify if I would like to get a full grade. Okay, so I will pretend that so my idea, I have two contradicting goals. So first idea, simplify as much as possible. And in many cases, when you try to simplify, even if you know nothing about Lagrange multiplier methods, many problems that can be solved basically by high school students. So, well, okay. So imagine that I skipped the possibility to simplify. Now I will standardize. So I will say maximum x plus y plus 2z, subject to I'm standardizing my task, that is 10 minus x squared minus y squared minus z squared greater or equals than 0, and x plus 2y plus z is equal to 0. Now let's check IndCQ. The problem with IndCQ that I have not yet solved the problem, and it may happen that both constraints are satisfied as equality constraint. What may happen in a suspicious point? The second one should be constraint should be equality. But the first constraint, I don't know yet. Maybe because I have not solved the problem, I don't know yet whether in suspicious point the first condition will be satisfied as equality, or maybe the first constraint will be satisfied as strict inequality. Okay, for the moment, I haven't solved the problem, and I don't know whether the first constraint will be satisfied as equality or as strict inequality, while the second condition for sure will be satisfied as equality. That's okay?
Me, I have a question.
Yeah.
So, like the first condition is x squared plus y squared plus z squared is less or equal to 10. But
yeah,
if we want to maximize the sum that we're given, shouldn't they be equal to 10? Because like if they're less than 10, then probably we did not maximize the first sum.
Yes, I've exactly have discussed this problem, that if you can simplify the problem, then simplify it. But I'd like to show you how to work with inequality constraint when they cannot be simplified. Yeah, I have two goals.
Yeah, because I thought that like, the simplification that you showed is the only possible. Yeah, I'm very sorry. Okay.
So the main idea, there are many simplifications that can be done when you just think a little bit about the problem. So my first advice is to simplify if possible. But my second idea, we'd like to discuss what can we do if we do not see the way to simplify. So on real exam, I will simplify as much as possible. Decrease the number of variables, transform inequalities if they can be transformed into equalities, and transform inequalities inequalities into equalities if possible. Sometimes it's not possible, but if possible, so then transform. In this case, by the way, you are wrong, because we have the second constraint. You cannot be sure that x squared plus y squared plus z squared is exactly 10. You would like to have a big X, big Y, and big 2Z. You are right. But if you have only first constraint, then you are right. It will be satisfied as equality. But we have two constraints, and maybe second constraint does not allow x squared plus y squared plus z squared to be exactly 10. So even we cannot be sure that with second constraint it's exactly.
Thank you. Yeah, thank you.
Okay, so for the moment I will not do simplifications. Why? Imagine a situation on the exam when you just have not noticed the possibility to simplify, or on the exam in the text it's written, use Lagrange multiplier method with inequality constraints, and then you cannot simplify. Okay, so in DCQ, because for the moment I don't know yet whether I will have first constraint satisfied as equality, or whether I will have first constraint satisfied as inequality, I need to check two versions of InDCQ. So I have two versions of InDCQ. So let's call it version A, and this will be version B. Okay. So in DCQ, I need to check in DCQ version A, and I need to check in DCQ version B. Let's discuss them. You have already solved last year, you have already solved in DCQ with equality constraint. So now imagine version A. Yeah, imagine version A. We construct, so in version A, we have two equality constraints. So in version A, the matrix of first derivatives, okay, let's write, this will be G1 of x, y, z is greater or equal than 0, and this is G2 of x, y, z is equal to 0. So when I check in DCQ for version A, my matrix of first derivatives of equality constraints, and in version A I have two equality constraints, will be minus 2x minus 2y minus 2z, and the derivatives of the second equality will be 1, 2, and 1. And my question is, what is the rank of this matrix? If it's 2, then I'm happy. In DCQ, in version A is satisfied. Version A, 2 equality constraints. So let's call this 1, 2. 1 is active. Active, I mean equality. And inequality 2 is, constraint 2 is active. Active, that's a word for equality. Okay, what is the rank of this matrix? Can the rank be, let's say, can the rank be 1?
Yes.
Yes. At point minus 1, minus 1, minus 1.
Okay, if rank 0 is not possible because I have non-zero line, let's check whether rank 1 is possible. So it should be minus 2x divided by 1, should be minus 2y divided by 2. I should have minus 2z divided by 1. And because I'm checking version A, in version A, I should have both equality constraints. I should have in version A of InDCQ, both constraints are active. X plus 2y plus z equals to 0. Okay, let's check whether whether this can be. So I see that z is equal to x, and y is equal to 2x. Yeah, and z is equal to x. Y is equal, z is equal to x. Y is equal to 2x, and no, that cannot be, yeah, because they should be all 0. 0 plus 0 plus 0 is 0, and 0 squared plus 0 squared plus 0 squared equals to 10. That's wrong. Yeah. So rank 1 is not possible. is not possible. And now I see that rank of J is equal to the number of active. Active means equality of active constraints, and so in DCQ version A is satisfied. Okay, I'm happy with IndiCQ version A. Any questions, or we may go on?
Let's go on.
I have a question. For these simulations, we assume x, y, and z are approximately equal to or approach to each other, right?
Sorry, I have just because in the beginning, before I know suspicious points, I have two opportunities. Either first inequality is equality, either it's strict inequality. And so I check version A when both constraints are active, are equalities. Then I will check, in a moment, we will check version B. What's your question? We have not checked version B yet.
Yes, thank you.
So now we will check version B. I don't know yet, but I think that will be okay. NDCQ version B. Version B says that 10 minus x squared minus y squared minus z squared is strictly greater than 0, while x plus, oh my god, I don't remember that. On the whiteboard, it's much more easy. 2y plus z. 2y plus z is 0. Okay, I create the matrix of first derivatives, but like previous year, we take care about equality constraints. In version B of IndiCQ, only one constraint is active. This is active. Active means equality constraint. This is non-active constraint. Okay, I create a matrix, Jacobian matrix of equality constraints, and it is 1, 2, 1. What is the rank of this matrix? It's 1. And it's equal to the number of active constraints. When the rank is equal to the number of active constraints, then IndiCQ is satisfied. IndiCQ version B is satisfied. Okay, have we done step 3? So first step is to avoid solving inequality constraints problems. Step 2 is standardize. Step 3, check IndiCQ all possible versions. So for example, if I have 2 inequality constraints, then I need to check IndiCQ 3 times, when both are active, when the first is active, when the second is active. Okay, if I have 2 inequality constraints, then I need to check 3 versions of IndiCQ.
Should we check the case when both inequalities are inactive?
If both inequalities are inactive, then you have no Jacobian matrix and the rank is 0, so that's automatically satisfied. If you have, so in DCQ, there are no in DCQ in problems without constraints. So if you have no, or if you consider the case of no constraint, you have 0 active constraints and you have no Jacobian matrix that automatically satisfied.
Okay, I understand, thanks.
Excuse me,
Okay,
can I
let's,
ask one question?
yeah.
So in DCQ version B, one of the constraints is equality, while the other one is inequality. So we do not include them in Jacobian, yes?
Yeah,
we don't include
Jacobian will be for equality constraints. So yeah, let's stress it once again. Let's stress it that Jacobian matrix is like previous year. How have you constructed Jacobian matrix? It was Jacobian matrix of equality constraints. So the only difference, and that we do not know before solution which version is fine. So we check all versions of IndiceQ. So the procedure is exactly like previous year. So Jacobian matrix is constructed for active, that means equality constraints. But
I'm sorry, can I ask a question?
Yes.
And so if we have n constraints, can we generalize somehow how many Jacobian matrices will have to be checked?
If you have, in general, if all your original constraints are inequality, like greater or equals n zero, then you have 2 to the power n minus 1.
Okay. And if some constraints are not inequalities but simply equalities, does it change?
Include them for sure in. So we include them for sure, and that means 2 times less the number of opportunities.
So it will not be 2 to the power of n minus
2 to the power n minus 1 minus 1. So if you have, imagine 3 inequalities, like, and 2 equalities, so this will be included for sure in Jacobian. And then we have this, like, will be equality, 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 inequality, 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 equality, inequality, and by 2, and it will be 1, 2, 3, 4, 5, 6, 7. So it will be 2 to the power 3 minus 1.
Thank you.
Okay, let's move on to the first order condition.
Ask you the last question.
Yeah.
So when we have like both active and non-active constraints, we take care only about active, right? So we don't care about non-active.
Yes.
Yes.
Perfect.
Thank you.
Okay, let's move to Lagrangian function. Our problem is standardized. So for standardized problem, so let's go to, I don't know, it's first order conditions. I don't remember, it was first it was avoid problems, then it was standardized, then it was IndiceQ, so it's step 3. Okay, first order conditions. We have a standard problem like maximize f. We have some h1 is exactly equal to 0, h2 exactly equal to 0, g1 is greater than 0, g2 is greater than 0. Maybe there are some more, but they are all of the standard form. They have equalities or inequalities, but no other types are possible. I have a standard problem. So I will discuss only that type. If you have another type, then transform it into this type, and you have a procedure. Okay, I will do Lagrangian function. It will be f plus all the type equalities. I will use mu as Lagrange multiplier. For new type inequalities, I will use lambda. So I will use mu1, mu2, and so on. These will be Lagrange multipliers for equality constraints. And for inequality constraints, I will use lambda 1, lambda 2, and so on. And so in my case, I have a Lagrangian function f plus mu1 h1 plus mu2 h2 plus lambda 1 g1 plus lambda 2 g2, and maybe there are some more terms. In my case, and what will be the first order conditions? What are the first order conditions? DL with respect to dx is 0 for all x. dl with respect to d mu is just h, that should be 0 because h is an old type equality constraint. For all mu. dl with respect to d lambda is just g. G should be non-negative for all lambdas. So if you remember last year, there was no requirement for the sign of mu. If you remember our intuition, we have discussed that lambdas should be non-negative. So no such condition for mu, but we have such condition for lambdas, for all lambdas. And finally, lambda I times gi should be 0 for all lambdas. That's basically all. We have first order conditions.
Можете наверх, пожалуйста, промотать на секундочку?
Yeah.
Еще чуть-чуть, буквально. Спасибо.
Maybe I can do it, maybe it would be better like this. I don't know. This is better or this is worse?
No, it was all like that, I believe.
So how should I keep, like vertical or horizontal?
Like the previous one.
Horizontal, please.
Yeah, great, thank you.
Okay, let's go back to our problem. Yeah. Yeah, can we go?
Well, let's do it.
I'm sorry. And would you please remind why all lambda et have to be greater or equal than 0?
We have discussed it last time. So the basic idea that so it's better to so if you are allowed to go you are allowed to go into that region inequality, and so this region is not allowed, and this region of space is allowed. So basically the gradient of a function you're trying to maximize. So to have a point on the border, the gradient of the function. So imagine you have a problem like you are on a line. So on a line, you should the function f may increase in that direction, and the function f may increase in that direction. That's okay. That point may be optimal because this is okay and that is okay. Why so? Because you cannot move from a line. You would like to go there, but it's not possible. You are in a local extrema. You'd like to go there, but it's not possible. You are in a local extrema. And when you speak about inequality constraint, can the function f grow in that direction? Yes, you are not allowed to go there. You would like to go there, so you are standing in a best point. You would like to go there, but you are not allowed to go, so you are in the best point. But the case when you are in a best point and the function grows in the direction where you are allowed to go, that is not possible because you would just go in that direction and increase the value of f. Okay, so this is okay, that f increases and that is the maximum, and that is a bad situation. That means you are not in extrema. If you are allowed to go into the direction where f grows, then you will just go there. Okay.
Yeah, fine. Thank you very much.
The idea is that you should be prohibited to go into the direction where f grows. And I imagine that gradient, this is a gradient of g. This is a gradient of g. And when they look, sorry. Yeah, like this. Gradient of G, yeah, the same is allowed. Yeah, okay. Let's move on to our example. In my case, my L will be, oops, I don't remember what was my function. It was something like x plus y plus z, yeah? Am I wrong? I don't remember, honestly.
X plus y plus 2z.
Plus 2z. I remember then it was plus mu times x plus 2y plus z, yeah? And plus lambda 10 minus x squared minus y squared minus z squared. In my case, this is H, this is equality constraint, this is G, this is inequality constraint, and this is my F. Everything is fine. I don't remember. I don't like to go back and to copy. Just if it's not okay, just let's solve this problem. Or that's fine. Numbers are the same.
Yeah, everything correct.
Okay, so now let's write all the first order conditions. First, like old conditions, dl with respect to dx is 1 plus mu minus 2x lambda, that is 0. dl with respect to dy is 1 plus 2 mu minus 2y lambda, that is 0. So just old conditions, like equality conditions. dl dz is 2 plus mu minus 2z lambda, sorry, that is 0. What else? Old conditions. Obviously, my equation should be satisfied, yeah? dl with respect to d mu, that's the original requirement, yeah? And finally, these are old conditions, yeah? These are old equality conditions. And now something new. First, dl with respect to d lambda is 10 minus x squared minus y squared minus z squared, and that should be greater or equal than 0. Then lambda should be greater or equal than 0, and then lambda times 10 minus x squared minus y squared minus z squared should be 0.
Yes,
yeah.
In the fourth line, it's dl dmu. It's x plus y plus 2z. Oh, no, sorry.
Maybe I have confused something.
My mistake. It's my fault. Excuse me.
Okay. That's good to ask questions. You are right. So if you have doubts, then just say me, because I may be wrong. Okay, that's a big system. How to start to solve it? I strongly advise you to start to solve. So you are free to solve in any way. So if you see, oh, I see how to solve it, then I have no. So we live in a free country, and you are free to solve it as you wish. But my advice is to start. So that's only advice. So if you know how to solve, start from that one. So that's advice. It's not. So if you see how to solve it, no problem. So advice, start from lambda time dl d lambda equal to 0. Why? Because you have a product that is 0. And if you have a product that is 0, then you obviously have two cases. And that simplifies greater solution. So basically, my advice, start from that case. So we will consider case case 1, lambda is 0. And case 2, case 2, dl d lambda is 0. So that's only advice. If you see, for example, I can subtract mu from first and third, and it will be simplified, then okay, you are right. That's not a problem. So
Excuse
main
me.
idea. Sorry.
Because in our equation, which is in the red circle, we use lambda to multiply another sentence, which is the consequence is 0. So why do we use lambda here? We do not use it or do not use it.
Sorry.
Excuse me, because we use lambda to multiply another sentence, which the answer is 0. So what's that? So why do we use lambda here? Because we already assume lambda is not 0.
Where we assumed lambda is not 0.
It's bigger or equal to 0.
Yeah,
then we
but
have
it makes 0.
in the circle.
I don't understand your point. You'd like to write here lambda greater than 0. You'd like to consider cases by that?
No, I mean, the big equation in the red circle is equal.
Let's call it 1, 2, 3, 4, 5, 6, 7. Yeah, number 7.
Sentence is number 7. And lambda for now in definition is bigger or equal to 0.
Yeah.
But this equation equal to 0. So why do we use lambda here? Because we do not use lambda, this equation will still equal to 0 or not. Or we will never find the certain number for x, y, and z. Because it will different solutions.
We only start from that. Yeah, let's continue. Okay, so I have 2 cases. Let's continue. Let's solve it completely. So first case. So first case is very easy. Lambda is 0. If lambda is 0, first case 1, lambda is 0. So in that case, what do I have? This will be 1 plus mu is 0. The second one will be 1 plus 2 mu is 0. And I'm too lazy to solve it because I see a contradiction. Yeah. When I consider the case lambda is 0, I obviously see that it cannot be, lambda cannot be 0 because this gives me mu equal to -1/2. That gives me mu, -1. And that is mu -1/2. I clearly see a contradiction. So case 1 doesn't work. Okay, let's move on to case 2. Case 2, lambda is positive. And if lambda is positive, then I can simplify the equation, the inequality number 7. I can simplify, so I will copy. Now I think 1 plus mu plus, oops, I forgot. I need to copy. Okay, so let's work with that case. Okay, so in that case, 7 will be, number 7 will be simplified to 10 minus x squared minus y squared minus z squared is equal to 0. Okay. Now we have only first, second, third, fourth, and let's okay, now we know that lambda is positive. And now let us find lambda. We will find the equation for lambda. And I think we will be more or less happy with that. So from first equation, lambda is 1 plus mu divided by 2 x, I think. Yeah.
Yeah.
Yeah. From the second equation, I think lambda is 1 plus 2 mu divided by 2y. From the third equation, 2 plus mu, 2 plus mu divided by 2z is lambda. And yeah, I think, yeah, I have found x is, yeah, it's 1 plus mu over 2 lambda. Y is 1 plus 2 mu over 2 lambda. Z is 2 plus mu divided by 2 lambda. Then I plug into equation number 4. So I have so let's remove that. That's a wrong approach. So that's okay. They are satisfied, but the idea is so okay. I have found from 1, 2, 3. I have found that. Now I plug in into equation number 4. I have 1 plus mu over 2 lambda plus it was like 2 times 1 plus 2 mu over 2 lambda plus 2 plus mu over 2 lambda is equal to 0. Yeah. Everything is okay? Because it's very difficult for me. I don't see the original system and I try to remember it by heart. But
yeah, I'm still looking at it. No, it's
okay, we multiply by 2 lambda because we are solving case 2 when lambda is positive. So I don't care about and finally I have 1 plus mu plus 2 plus 4 mu plus 2 plus mu is equal to 0. And mu is finally minus 5 over 6. Woohoo! I have found mu. Let's go on.
Yeah, of course.
Okay, let's go on and find lambda. We plug these x, y, and z in equation number 7. Oops, I will copy them on a sheet of paper. X is 1 plus mu over 2 lambdas, y is 1 plus 2 mu, and z is 2 plus mu. Okay, let's move on. And we plug x, y, z into equation number 7. And we will have 1 plus mu divided over 2x squared plus, sorry, 2 lambdas, plus 1 plus 2 mu divided by 2 lambdas squared plus 2 plus mu over 2 lambdas squared is equal to 10. Yoo-hoo! I have lambda. I have lambda. I see that if I see that lambda squared is just, I multiply by lambda, both sides by lambda squared, and I divide by 10. So I have 1 over 10, 1 plus mu over 2 squared plus 1 plus 2 mu over 2 squared plus 2 plus mu over 2 squared, and this is lambda squared. Because I'm solving case 2, lambda is positive, then I have lambda. Lambda is a square root, and this is just, you recall that mu is equal to minus 5 over 6. So it is 1 over 6 divided by 2 squared. That is 1 minus, so 6 minus 5 minus 5, as I think it will be minus 4 over 6 over 2 squared. And that will be 7 over 6. Yeah, 7 over 6, I think. Yeah, 7 over 6 over 2 squared. And then finally, I have lambda is equal to square root of 1 over 10, 1 over 12 squared. Here I have 1 plus 4 squared plus 7 squared. And I think I'm more or less happy with lambda. Lambda is 1 over 12 square root. I have it's 66. Yeah, 50 plus 16, 66 over 10. And if I'm not mistaken, it's just square root of 33 over 5. And that cannot be much simplified. Oh, that's okay. I'm happy with lambda. And now I have, yeah?
Where did you get mu from? How did you find it?
On the previous page.
Ah, okay, all right, yeah, sorry. Thank you.
And now we have x, y, and z. Yeah, we have x, y, and z. Because I have mu, I have lambda, I won. We have only one suspicious point. So mu, lambda are found. And then we have x, that is 1.
1 plus mu divided by 2 lambda.
Yeah. 1 plus mu divided by 2 lambda. That gives me, but I don't care. So I hope when you know mu and lambda, then you can find all this stuff. That's not a problem. That should be not a problem for you. Yeah, that's okay. So just you know lambda is here, mu is 5 over or minus 5 over 6. Yeah, it was minus 5 over 6. Okay, so suspicious point is found. So we are great. Yeah, we have solved first order conditions for our problem. Yeah.
Sorry.
Yeah.
So I think that since we have inequality constraints greater or equal to 0, I think that in the first order conditions, lambda should be less or equal to 0.
No.
So,
no.
But like last lesson we did.
No, it was greater than 0.
But there was a constraint less than 0 in like last.
But when I have included it into Lagrangian function, it was okay. It depends how you include. It basically, the main idea is not how it's written. The main idea is how it's included in Lagrangian function. So you may even what is it? So the idea is how it is included in the Lagrangian function. If you look carefully, what you should have. So what does really matter is the following point. I have maximum problem. I have j greater than 0, and in Lagrangian function I have plus lambda times g. So that is important. Maximum greater than 0 plus lambda times g. For example, I can do it in my head without even you notice the standardization. I can do standardization, so like hidden standardization. So, for example, imagine that I have maximization problem with g greater than less than 5. It seems at first it's not standardized, yeah, but in Lagrangian function, I write plus lambda times whoop, and without, so it's magic. I write 5 minus g. I have done standardization without even your notice. You see that basically what I have included here in a Lagrangian function is 5 minus g, and it's standardized, but just I haven't written it explicitly. Okay.
Yeah, I see, but so if I see the graphical solution, so I thought that actually the gradients should be in the opposite directions. So
the gradients of which functions? It depends. do you speak about, so let's call it G star, and that is will be G star. G star is 5 minus G. So if you speak about the gradients of G and F, they are in opposite direction. If you speak about gradients of F and G star, they are in the same direction. So you should be careful whether you speak about gradients of that function or this function.
Okay, thank you.
So yes, but you should be careful. But basically, you are right. You may do so. The only thing that counts is how do you include this in optimization problem in Lagrangian. So my idea is this is the first thing. I will always do maximization. Second, I always write like this. I include with plus, and I write this exactly as it was written in inequality. But I can do something in my head. So if I have G is less than 5, obviously I see that the form to standardize is 5 minus G, and I do not spend time on copying. I do not just explicitly write 5 minus G, but when I include in Lagrangian function, I think about this. Okay, so that's just a matter. Everything is consistent with the previous lecture. So I may do some arithmetic errors that happens, but the direction is right of G. Yeah. Okay, now let's move on to our next problem. Sorry, not next problem, condition number. So classify. I think it was step 5, maybe. Classify suspicious point. So we have one suspicious point. That is the point. That is the point A. We have one suspicious point, and we need to classify it. We will work with second order conditions later, but so we may use bordered Hessian techniques, and maybe some of you will guess that in Hesse matrix we will include which inequalities? Active, non-active?
Active.
Yeah, basically the procedure will be the same, but we will, as last year, but we will include active constraints in Hesse matrix. Basically, that's all. And condition will be the same. Just you need to be careful. In one point, you may have a bordered Hessian of size 3 by 3. In point B, you may have a Hessian matrix of size 4 by 4. That may happen because in point A, you have one condition that is equality and active, and in point B you may have two conditions that are active. In my case, I'm too lazy that I have one point, but my matrix will be three variables, two constraints. It will be 5 by 5 if I use a bordered Hessian matrix. So I'm too lazy to do a matrix 5 by 5. So I will use a Weierstrass. Sorry, I missed letter Weierstrass theorem. Once again, I have constraints that are x plus y, x plus 2y plus z is equal to 0, x squared plus y squared plus z squared is less than 10. This is a plane. This is ellipse. Yeah, it's ellipsoid. So sorry, it's not an ellipsoid. It's a sphere. Yeah, it's a ball. It's a plane in a ball. If I intersect a ball with a plane, so in intersection, I will see just a circle. So geometrically in 3 dimensions, I have a circle. And Weierstrass theorem says me, yeah, you have bounded closed set, so your function should have a maximum, should attain a maximum value there. And I have one suspicious point. Yeah, Weierstrass theorem says me, you should have one, so the function should attain maximum value. And I have one suspicious point. Like one? Yeah, so Weierstrass theorem, the function f is continuous. Continuous. The function f is continuous. Okay, my set D is closed and bounded. Classify points. So my function f is continuous. I checked that my set D is closed and bounded. That is satisfied. So Weierstrass theorem says me your function has the function f. So this is my D. So Weierstrass theorem says me that f attains the extremum, the maximum. And I have one suspicious point. So we have a conclusion that our A is a maximum point. Local maximum. We don't. No, even global. Local and global, because we are not using second order conditions with Hesse matrix, but it will be maximum local and global. Okay, any questions?
Excuse me, is it like a local maximum or a global?
Local and global, because we are helped by Weierstrass theorem. When you use Hesse matrix, you check only local constraint extrema. But when we are using Weierstrass theorem, it's local and global.
Like global on this constraint.
Yeah, global on this constraint.
Okay, thank you.
So you may have local on the constraint. So maybe there is another point on the constraint with another local maximum, which is bigger than my local maximum constraint. But in this case, that's a global on constraint.
Excuse me, I have a question. For this, because we calculate lambda, x, y, and z, at first we assume that all these values are exist. Is there any kind of case which we have a function, but after we solve it, we figure out this kind of value doesn't exist? Like lambda doesn't exist, or x and y cannot be a real word?
I don't understand your question. Sorry, could you restate it? Maybe?
Sorry, I mean, time before we solve the solutions and the functions, we assume lambda, x, and y, and z, they are exist. And is there any kind of cases after solving all these equations, we figure out lambda, x, y, and z, they
have figured lambda. Yeah, we have figured lambda, x, and y, and z, and mu. We have found all 5 unknowns. Yes. And what is the problem?
I mean, could you give me an example? Because all the solutions we solved today, we have answers.
I don't see your point. Maybe could you write in the chat your question? Maybe I don't. I'd like to help you to answer your question. Yeah, we have only one example of maximization problem. Yeah, we will do more, but could you give me an example with no answers? to try to solve at home. What do you mean? An example with, so you'd like to have a practice, or example with no answers, lambda or x could not exist at the same time. Yeah, obviously you can have something like maximum of x plus y plus z given x plus y plus z is greater than 5. In this problem, you will have no solutions because, yeah, sometimes it may happen that there are no maximum point at all. Yeah, that may arrive. The example of a problem with no solutions is obvious. If I try to maximize x plus y plus z given that x plus y plus z is greater or equal than 5, obviously there are no solutions. I can make my extrema as big as possible. So in this case, you will not find, so if you construct the system of first order condition and you will say, oops, no solutions. That may, yeah, that may happen. I don't understand what do you mean lambda exists. You will have a system like L x plus y plus z plus lambda times x plus y plus z minus 5. In first order condition, you will have dl dx is 0, dl dy is 0, dl dz is 0, dl d lambda is greater than 0, lambda is greater than 0, lambda times dl d lambda is equal to 0. And if you try honestly to solve this system, you will have no solutions of this system of 6 equations. There are no solutions in this system.
Yes, thank you. That's my question.
Okay, and it's lambda. It's lambda. Maybe I'm not pronouncing it well, but it's lambda. Okay, so have a nice weekend. See you next time.
Nice weekend. See you. Bye-bye.
Thank you very much.
Простите, а можно задать еще один вопрос? Ну,
можно.
На русском. Все-таки, когда мы говорим, что у нас лямбда больше нуля и лямбда меньше нуля, в зависимости от ограничения?
Смотри,
Или она
проще
всегда
запомнить
больше
это
нуля?
так. Смотри, еще раз. Если ты пишешь ограничение, если ты пишешь функцию в максимум, если ты пишешь ограничение g больше либо равны нуля, если ты в функцию Лагранжа вставляешь плюс лямбда на g, вот если ты выполнил это, то тогда в условиях первого порядка ты пишешь лямбда больше либо равно нуля. А дальше работает правило там, ну, смены знаков, что если ты что-то одно поменял, ну, там что-то одно поменяй. Но если это всегда стандартизировать и писать так, ну, то есть теоретически ты можешь сказать, а я вот так вот, а я вот буду решать задачу на максимум, g будет больше либо равно нуля, а я вот такой вот артхаус у меня, я буду писать это минус лямбда g. Ну, то, что ты обозначил лямбда, обычно означает минус, ну, минус лямбда. И тогда в условиях первого порядка будет лямбда меньше либо равно нуля.
Ага, все, понял. Мы, между прочим, на семинарах всегда записываем минус лямбда же.
Ну, можно и так.
Все, хорошо, понял. И еще такой...
То есть ты можешь сменить знак нечетное число, в смысле четное число раз. Ну, например, ты можешь решать, ну, четное. Раз, два, или вот эти две, или вот эти две, или вот эти две, или вообще все 4 поменять. Ну, то есть принцип, на мой взгляд, проще запомнить, когда все с плюсом, тебе не надо думать, ой, это с минусом, это с плюсом. Все с плюсом, такой жадный, такая мнемотехника. Я жадный, я хочу максимум, я хочу уже побольше, но я хочу плюс лямбда, и у меня лямбда побольше. Вот, и у тебя все побольше, ты запомнил легко. А хочешь для какой-то локальной задачи поварьировать, в 2 любых местах или в 4 можешь менять. То есть можешь сказать, решаешь задачу на минимум, g меньше либо равно нуля, L пишешь плюс лямбда, в условии первого порядка войдет лямбда больше нуля, ну, либо равно. То есть,
ага, все понял.
Мне кажется, что проще всего запомнить так. А дальше от этого, ну, 2 любых знака можно поменять. Или 4.
Ага, понял, большое спасибо. Еще такой, мне кажется, глупый вопрос, но все-таки, если мы минимизируем функцию, то что-то меняется или нет? Или минимизация не имеет никакого смысла, в принципе?
Ну, почему? Ну, у тебя есть 2 стратегии. Либо перевести задачу минимизации к максимизации, либо воспользоваться здесь, что вот 2 знака можно менять. Минимизация, ну, например, можно написать минимизацию, один знак поменял, g больше либо равно 0, здесь Лагранж плюс лямбда g, и тогда в условиях первого порядка будет лямбда меньше 0, потому что я поменял в 2 местах.
Так, вот сейчас не очень понятно. То есть если мы минимизируем нашу функцию...
Смотри, еще раз, у тебя 4 точки. 4 точки, за которыми ты следишь. 1, 2, 3, 4. Меняешь 2 любых точки. Хочешь вместо максимум минимум? Пожалуйста. Тогда пиши лямбда меньше 0 в условиях первого порядка.
Ага, все, понял. То есть если любая из первых 3 точек меняется, то мы автоматически меняем знак у лямбды, правильно? Ну, ограничение.
Ну, не обязательно. Любые 2 можно поменять.
Любые 2,
Можешь
понял.
поменять у лямбда, можешь поменять. Ну, то есть, еще раз, можно вот это поменять на минимум, а вот это же меньше либо равно 0. И тогда там не будет меняться лямбда. Ну, то есть, меняется четное число знаков.
Ох, понятно. А вот в книжках, которых вы рекомендовали, можно это все прочитать и понять смысл?
Ну, я рекомендовал одну, наверное, книжку. Ну, да, на мой взгляд, Рангаранджан Сундарам хорошо объясняет.
Ага, ну то есть там несложно и нормально, да?
Слушай, ну, по-моему, это лучшее. Ну, то есть, может быть, есть где-то лучше. Но мне кажется, она очень... Там есть опечатки, но не считая опечаток, она, мне кажется, очень толковая.
Ага, все, хорошо, понял. Еще раз большое спасибо.
Пожалуйста. Все, тогда всем пока-пока.